For a few extraordinary minutes, noon forgets that it is day. The air cools, birds fall silent, and a black moon covers a star 400 times wider than itself, made possible only because that star is also about 400 times farther away. Along the narrow path of totality, sunlight breaks into Baily's beads, flashes as a final diamond ring, and then gives way to the ghostly corona. This perfect alignment feels eternal, yet it is slowly disappearing as the moon drifts farther from Earth each year. Thank you sincerely for spending this time here. Share in the comments what time it is where you're listening, and which place on Earth is beneath your sky. A like helps this quiet journey travel farther. A subscription keeps future mysteries close. And sharing the video may bring someone else into the shadow. Now, let the daylight begin to fade as the rare geometry of a solar eclipse unfolds. A solar eclipse begins with an arrangement so simple that it can be described in a single line. The moon moves between Earth and the sun. Yet when that alignment becomes exact, the familiar order of daylight changes with remarkable speed. The sun, which normally dominates the sky without interruption, begins to lose its shape along one edge. A dark curve appears against it. The curve widens, the bright disk narrows, shadows on the ground sharpen, colours begin to flatten, and the world enters a form of light that does not belong to morning, afternoon, or evening. Nothing has happened to the sun itself. The transformation comes from position alone, from three bodies reaching the right geometry at the right time. In that brief geometry, a shadow crosses a planet. The moon is in its new phase during a solar eclipse. The side facing Earth receives little direct sunlight, so the moon is mostly hidden in the brightness of the daytime sky. Most new moons pass without visible drama. The moon travels near the sun from Earth's point of view, but it usually moves slightly above or below it. During an eclipse, that ordinary near passage becomes a direct crossing. The moon's dark disk covers part of the solar surface, and in rare places it may cover the whole visible face of the sun. The motion behind it is slow, measured, and predictable. Earth turns. The moon follows its orbit. Both continue along paths shaped by gravity. The eclipse is not an interruption of those motions. It is one of their most precise results. The scale of the alignment is difficult to hold in a single thought. The sun is a star, an immense sphere of hot plasma whose diameter is roughly 400 times greater than that of the moon. The moon is a comparatively small rocky world, but distance changes apparent size. The sun also lies about 400 times farther from Earth than the moon. These two proportions nearly balance. The much larger object is much farther away, while the much smaller object is much closer. From Earth, the disks of the sun and moon therefore appear almost equal in width. That match is not perfectly fixed. Earth does not travel around the sun in a perfect circle, and the moon does not travel around Earth in a perfect circle. Their apparent sizes change slightly as their distances change. At some eclipses, the moon appears large enough to hide the sun completely. At others, it appears slightly too small, leaving a ring of sunlight around its edge. Even so, the overall resemblance remains extraordinary. A nearby moon and a distant star occupy nearly the same space in the sky. The result is an eclipse with a sharp dark boundary, a moving shadow, and, under the right conditions, a complete disappearance of the solar surface. The first stage of an eclipse does not look like darkness. It looks like subtraction. A small portion of the sun is missing, though the surrounding day often remains bright. Human vision adjusts so easily that much of the early change can pass unnoticed. The uncovered part of the sun still provides intense light. The landscape may look almost normal, even when a significant part of the solar disk is hidden. yet instruments register the decline. Sunlight passing through gaps between leaves forms many tiny images of the partly covered sun on the ground. These bright shapes become crescents. Straight edges and ordinary shadows gain an unusual clarity. The light no longer arrives from a full round source. It comes from a narrowing shape in the sky. As the moon advances, the atmosphere does not darken in the same way it does at sunset. During sunset, the sun moves toward the horizon, and its light crosses a longer path through the air. Red and orange wavelengths become more prominent as shorter wavelengths scatter away. During an eclipse, the sun remains above the horizon, but less of its surface is visible. The light fades while still arriving from high in the sky. This creates a different sensation. The illumination weakens without the usual colours of evening. The horizon may remain bright beyond the moving shadow, while the area beneath it takes on a grey or metallic tone. The change can seem both gradual and abrupt, because the early stages are subtle and the final stages are rapid. Temperature often begins to fall as the solar disk shrinks. The ground receives less energy, and the air near the surface slowly responds. Breezes may shift as local heating changes. The overall pattern is consistent. The environment reacts to the temporary loss of sunlight. A solar eclipse is therefore not only something seen in the sky. It moves through the lower atmosphere and across the surface. It alters brightness, warmth, contrast, and behavior. The alignment is astronomical, but its presence becomes physical at ground level. The shadow itself is not a single uniform region. The moon blocks sunlight in different degrees, creating separate zones that travel across Earth. In the broad outer shadow, only part of the sun is covered. Within the narrow central shadow, the bright solar surface can disappear entirely. These regions move because the moon continues along its orbit while Earth turns beneath it. The shadow does not remain fixed over one place. It sweeps across oceans, mountains, cities, fields, and clouds, tracing a path determined by the exact positions and motions of the sun, moon, and Earth. From space, the effect appears as a dark patch moving over the bright face of Earth. From the ground, it is experienced from inside that patch, where the change in light seems to gather from all directions. The shadow may approach across the landscape too quickly for its motion to be followed in detail. Distant regions can darken first. The sky may lose brightness unevenly. Near totality, the remaining daylight collapses with surprising speed. The event that began as a small curve against the sun becomes a vast moving darkness. Yet even the word darkness requires care. During a total eclipse, the sky does not always become as black as midnight. The horizon beyond the central shadow can glow because sunlight still reaches areas outside the path. Planets and bright stars may appear. The sun's outer atmosphere, normally hidden by the brightness of the solar surface, can become visible as a pale structure around the moon. The result is not the absence of all light, but a sudden rearrangement of it. The main source is concealed. Fainter things emerge. The sky reveals layers that ordinary daylight erases. The rarity of the experience at any one place deepens its effect. Solar eclipses occur somewhere on Earth with regularity, but the narrow path of a total eclipse covers only a small portion of the planet. Most locations lie outside that path during any given event. A city may wait centuries between total eclipses. Even though partial eclipses are more common, the alignment must be correct on a planetary scale, and the observer must also stand inside the right moving shadow. The event depends on both celestial precision and geography. For this reason, a total solar eclipse feels larger than its duration. The central darkness may last only a few minutes, yet it carries the weight of long orbital cycles, vast distances, and rare coincidence. The sun is vastly larger than the moon. The moon is vastly closer than the sun. Earth turns under a shadow only a small part of its surface can enter. Every element is moving, and still, for a short interval, the arrangement becomes exact. That exactness is the first mystery of the eclipse. It is not mysterious because its cause is unknown. The cause is well understood. The positions can be calculated. The path can be predicted years in advance. The mystery lies in the way known motions create an experience that feels almost impossible. A small dark world crosses a distant star. Daylight weakens without sunset. A moving shadow touches Earth. The sky, usually stable in its brightness, reveals how dependent every ordinary scene is on a direct line to the sun. The first dark curve across the solar disk is therefore more than the beginning of an astronomical event. It is the visible edge of a shadow extending through space. It marks the moment when distance, scale, and motion begin to overlap. The moon continues forward. The remaining sunlight narrows. The ordinary day gives way, step by step, to an alignment that has been forming long before anyone beneath it can see the first sign. What appears to begin in the sky has already been written into the paths of worlds. The eclipse becomes possible not because the sun and moon are similar objects, but because distance disguises their true difference. The sun is a star, vast enough to contain more than 1 million worlds the size of Earth. The moon is a small rocky body, less than a quarter of Earth's width and silent under an airless sky. One burns through nuclear fusion, releasing energy from a core of crushing pressure and heat. The other reflects a small fraction of the sunlight that reaches its dusty surface. In physical scale, they do not belong to the same category, yet from Earth they can appear almost equal. The reason lies in apparent size, the angle an object occupies in the sky. A nearby object may look large even when it is small, while a distant object may look small even when it is enormous. The moon is close enough to spread across roughly the same angular width as the much larger sun. This is the quiet geometric balance at the heart of a total solar eclipse. The sun is about 400 times wider than the moon, but it's also about 400 times farther from Earth. These values are not exact at every moment, and the match changes as the bodies move along their orbits. Still, the proportions are close enough that the moon can cover the bright solar disk while leaving the outer atmosphere visible. If the moon appeared much larger, it would hide not only the sun's surface but much of the surrounding corona. If it appeared much smaller, it would never produce totality. The eclipse follows the same principle on a celestial scale. The moon, though tiny beside the sun, lies close enough to interrupt the line of sight. What makes the event unusual is that the foreground body and the background star appear so nearly matched. Their edges can approach one another with remarkable precision, producing moments when the moon seems to fit over the sun like a dark lid. That fit is never perfectly stable because the distances involved are always changing. Earth follows a slightly elliptical orbit around the sun, meaning its distance from the sun varies over the year. The moon also follows an elliptical orbit around Earth, moving closer during some parts of its path and farther away during others. When the moon is relatively near Earth, it appears slightly larger. When it is farther away, it appears slightly smaller. The sun's apparent width also changes, though less dramatically, as Earth moves nearer to or farther from it. A total eclipse occurs when the moon's apparent disk is large enough to cover the sun's apparent disk. An annular eclipse occurs when the alignment is direct but the moon appears too small, leaving a bright ring around it. The difference between these outcomes may come from a slight change in distance across hundreds of thousands of miles. From the ground, the result is immediate and visual. In one case, the sun disappears. In the other, a circle of fire remains. The near equality of the disks creates another remarkable effect. The sun's hidden outer atmosphere becomes visible. Under normal conditions, the solar surface is so bright that the corona is lost in its glare. The corona extends far beyond the visible disk, but it is much fainter than the light from the sun's surface. During totality, the moon blocks the bright disk while leaving the surrounding space exposed. A pale crown emerges around the black moon, shaped by the sun's magnetic field and filled with hot, thin plasma. This view depends on the moon being almost exactly the right apparent size. A larger moon would cover more of the inner corona. A smaller moon would allow too much surface light to remain. The same geometry that darkens Earth also creates a natural instrument, a moving mask that reveals a part of the sun otherwise hidden from unaided sight. Long before modern spacecraft, total eclipses gave astronomers rare opportunities to study the solar atmosphere. The balance did not always exist in exactly the same way, and it will not continue forever. The moon formed much closer to Earth than it is now. Over immense spans of time, tidal interactions have transferred energy through the Earth-Moon system. Earth's rotation gradually slows, while the moon slowly recedes. The change is small from one year to the next, but deep time magnifies it. In the distant past, the moon appeared larger in Earth's sky. Total eclipses would have been broader and more complete, with the lunar disk covering more of the region around the sun. In the distant future, the moon will appear smaller. Eventually, even at its closest approach, it will no longer be able to hide the sun completely. Total solar eclipses will end, leaving only partial and annular forms. The present age therefore occupies a temporary interval in which the sizes nearly match. The coincidence is not a permanent feature of Earth. It is a passing condition within the long evolution of the planet and its moon. This temporary nature deepens the eclipse without making it supernatural. No evidence suggests that the alignment was arranged for observation. It is the product of formation, gravity, tidal change, and chance. Yet chance in astronomy does not mean without cause. The moon formed through the vents in the early solar system. Its orbit developed through interaction with Earth. The sun's distance follows from Earth's orbit within the planetary system. Each part has a history. The apparent equality appears only when these histories are viewed from one particular surface at one particular era. Even on Earth, the equality is not exact across every eclipse. The sun and moon each span about half a degree, but their apparent widths shift slightly. That variation determines whether totality lasts for seconds or several minutes, whether the corona appears close to the lunar edge or farther beyond it, and whether a bright ring survives around the moon. A change too small to notice in ordinary night skies can alter the entire form of an eclipse. Vast bodies are involved, yet the outcome depends on narrow margins. The sun may be more than 100 million kilometers away, the moon hundreds of thousands, but from the ground their edges can meet with the delicacy of drawn circles. The match also changes through the brief minutes of the eclipse because the observer's position changes. Earth turns, the moon advances, the shadow crosses curved terrain. A person near the centre of the path sees a more symmetrical covering than someone near its edge. Near the boundary, the moon may conceal the sun for only a moment or fail to conceal it completely. A few kilometres can separate totality from a deep partial eclipse. The celestial arrangement may be almost perfect, yet the view depends on where the eye stands beneath it. This transforms the eclipse from a static alignment into a travelling geometry. The moon and sun do not simply overlap. Their apparent sizes, positions, and edges continually change as the shadow moves. Near totality, the remaining sunlight shrinks into a thin arc. Irregularities along the moon's surface begin to matter. Valleys allow beads of light to pass, while mountains block them. The moon is not a smooth disk, and the final light reveals its uneven horizon in silhouette. The apparent match is close enough that landscapes on another world can shape the last moments of daylight on Earth. Mountains no human eye can see directly become visible through their effect on sunlight. A ridge on the moon determines where a bead appears. A valley determines how long it survives. The cosmic scale narrows into topography. The eclipse becomes not only an alignment of spheres, but an encounter between specific edges. At totality, the dark moon may seem larger than the sun by only a small amount. Yet that small amount is enough. The solar surface vanishes, the corona unfolds, the sky dims, and the balance reaches its most complete expression. For a moment, the difference between a star and a moon is hidden by perspective. Their true sizes remain unchanged, but their apparent forms become nearly equal. The sight is created by distance, and distance is usually invisible. During an eclipse, it becomes visible through overlap. The moon shows how far away the sun is by matching it. The sun shows how close the moon is by disappearing behind it. Between them lies a coincidence measured not in similarity, but in proportion. It is a coincidence that changes slowly, fails often, succeeds only along a narrow path, and will one day pass away. For now, the sky still permits the fit. A small world crosses a star, and for a brief interval, distance makes them equals. A solar eclipse requires more than a new moon. It requires the new moon to arrive at one of the few places where its tilted path crosses the plane of Earth's orbit around the sun. This is why the sky does not darken every month. The moon completes a cycle of phases with dependable regularity. Each month, it moves from new moon to crescent, to half-lit, to full, and back again. At new moon, it passes between Earth and the sun in a general sense, but general alignment is not enough. Most of the time, the moon travels slightly above or slightly below the sun from Earth's point of view. Its shadow then misses the planet, passing into space beyond it. The three bodies are near a line, but not close enough to produce an eclipse. The reason lies in the tilt of the moon's orbit. Earth travels around the sun within an imaginary flat surface called the plane of the ecliptic. Most of the major planets follow paths that remain fairly close to this shared plane, a remnant of the broad rotating disk from which the solar system forms. The moon, however, travels around Earth on a path tilted by about 5 degrees relative to that plane. 5 degrees sounds small, and across ordinary human distances it would be. Across the distance between Earth and the moon, it is enough to separate the moon's position from the sun by many times the sun's apparent width. At most new moons, the lunar disk slips above the solar disk or below it. No visible crossing occurs. The moon remains hidden in daylight, and its narrow shadow never reaches Earth. The places where the moon's orbit crosses the ecliptic plane are called nodes. There are 2 of them. At one node, the moon moves from the southern side of the plane to the northern side. At the other, it moves from north to south. These crossing points are not objects or fixed marks in space. They are geometric locations created by the intersection of 2 orbital planes. A solar eclipse becomes possible only when a new moon occurs near one of these nodes. The timing must therefore satisfy 2 cycles at once. The moon must be in its new phase, placing it between Earth and the sun, and it must also be near a node, placing it close enough to the ecliptic plane for its shadow to reach Earth. If either condition fails, the alignment remains incomplete. This double requirement turns a monthly event into a rarer one. The same principle governs lunar eclipses. A lunar eclipse occurs at full moon, when Earth lies between the sun and the moon, but only if the full moon is near a node. Most full moons pass above or below Earth's shadow for the same reason most new moons fail to cover the sun. The tilt protects the sky from becoming mechanically repetitive. Without it, every new moon would produce a solar eclipse somewhere on Earth, and every full moon would produce a lunar eclipse. Darkness at midday and a reddened moon at midnight would arrive with each cycle. Instead, eclipses come in seasons. An eclipse season is a period when the sun appears close to one of the moon's orbital nodes. During this interval, a new moon can pass close enough to the sun's path to create a solar eclipse, while a full moon about 2 weeks earlier or later may pass through Earth's shadow and create a lunar eclipse. An eclipse season lasts only long enough for the necessary alignments to remain possible. Then the sun's apparent motion carries it away from the node, and the next series must wait for the geometry to return. These seasons occur roughly twice in a year, though the exact pattern shifts because the lunar orbit is not fixed. The nodes themselves slowly move. Their line rotates backward around the ecliptic over a period of many years, a motion known as nodal precession. This gradual turning changes where and when eclipses occur. It also helps produce the long repeating patterns that astronomers use to group eclipses into families. One of the best known is the Saros cycle, a period after which the relative geometry of the Sun, Earth, and Moon becomes similar again. After one Saros, an eclipse of a related character returns, though Earth's rotation places the shadow over a different region of the planet. The repetition is close, but not perfect. Each event belongs to a sequence that develops slowly, changing its path and form over centuries. Eclipses therefore reveal two kinds of order at once. The first is the short rhythm of phases, visible from month to month. The second is the slower rhythm of orbital crossings, node movement, and repeating alignments. The eclipse appears sudden from the ground, but its possibility grows from cycles nested inside other cycles. Astronomers can calculate these cycles because gravity governs the motions with extraordinary consistency. The Moon's orbit is affected by Earth, by the Sun, and to smaller degrees by other bodies, but those influences can be measured and modelled. The prediction of an eclipse is not a guess based on appearance. It is a calculation of where the Moon's shadow will be, when it will touch Earth, and how the moving planet will carry different locations through it. Centuries ago, eclipse prediction is more limited, but repeated observations reveal patterns. Ancient skywatchers noticed that eclipses return in recognizable sequences. They may not understand the full physical system, yet careful records show that the events are not random. Modern astronomy extends that pattern into precise maps, times, and paths. The tilted orbit that prevents monthly eclipses also makes each successful one more selective. The shadow does not simply fall anywhere. Small differences in the Moon's distance from the node determine whether the eclipse is central or partial. If the alignment is close but not exact, only the outer part of the Moon's shadow reaches Earth, producing a partial solar eclipse. If the alignment is tighter, the central shadow can touch the surface, producing totality or annularity along a narrow path. The node is therefore not a single switch between eclipse and no eclipse. It is the centre of a region of possibility. The closer the new moon passes to it, the deeper the alignment becomes. This is why one eclipse may cover only a modest part of the Sun in high northern latitudes, while another sends a central shadow across continents. The difference begins with a slight shift in orbital position. Earth's own curvature and motion then shape how that shift is experienced on the ground. The geometry also explains why an eclipse can happen somewhere on Earth, even when most people never see it. The Moon's shadow is narrow compared with the size of the planet, and much of Earth is covered by ocean. A perfectly valid eclipse may cross remote water, polar ice, or sparsely inhabited land. The alignment occurs for the planet, not for any particular observer. Human calendars divide time by days and months, but the sky follows overlapping orbital periods that do not fit neatly into those divisions. The moon's phase cycle is not exactly the same length as its return to a node. The mismatch causes eclipse opportunities to drift through the calendar. One year's eclipse season does not return on precisely the same dates the next year. The pattern moves, and over long intervals it circles through seasons and regions. This drift is another reminder that the eclipse is not tied to a date but to geometry. Dates merely record when the geometry arrives. The 5-degree tilt seems modest, yet it is responsible for the rarity that gives eclipses much of their power. It allows new moons to pass invisibly month after month. It separates the ordinary cycle of phases from the exceptional crossing of the sun. Then, when the moon approaches a node at the right time, the hidden structure of the orbit becomes visible. A path that cannot normally be seen announces itself by removing part of the sun. The eclipse reveals the location of an invisible plane, the crossing of an invisible line, and the precision of a motion continuing far beyond the scale of daily life. The sky darkens not because the monthly rhythm fails, but because several rhythms briefly agree. The moon reaches its new phase. It reaches a node. Earth lies beneath the shadow. For a short time, the usual near alignment becomes exact enough to touch a world. The shadow of the moon is not one simple cone of darkness. It has structure, edges, depth, and separate regions that determine what kind of eclipse reaches any place on Earth. At the center lies the umbra, the darkest part of the shadow, where the moon blocks the entire visible surface of the sun. Around it lies the penumbra, a broader and lighter region where only part of the sun is covered. These two shadows travel together, but they create very different experiences below. The umbra brings totality. The penumbra brings a partial eclipse. Their boundaries are drawn not by clouds or weather, but by straight lines of sunlight passing the moon and continuing across space. The difference between them begins with the fact that the sun is not a point of light. It is a broad disk. Rays leave from every part of that disk, and the moon interrupts some paths more completely than others. In the umbra, all direct rays from the visible solar surface are blocked. In the penumbra, only a portion of those rays are blocked, while the rest continue to reach the ground. The result is a shadow whose center is fully dark and whose outer zone is only partly darkened. On a wall close to a small lamp, an object may cast a sharp shadow. With a larger source of light, the edge becomes softer because different parts of the source remain visible around the object. The same principle operates across the distance between the sun, moon, and Earth, though on a planetary scale. The moon stands as the blocking object. The sun acts as the extended source. Earth receives the moving pattern. The umbra forms a narrow cone stretching away from the moon opposite the sun. Because the sun is larger than the moon, the sides of this cone converge, depending on the moon's distance from Earth. The cone may reach the surface or end before it. When it reaches Earth, observers inside it see a total solar eclipse. When it falls short, a different central shadow called the antumbra reaches the surface, and observers within it see an annular eclipse. Around both central regions spreads the penumbra, much wider than the umbra and able to cover a vast portion of the planet. This is why many more people may see a partial eclipse than totality. The penumbral shadow can touch entire countries, while the umbra crosses only a narrow corridor. From inside the penumbra, the moon appears to take a bite from the sun. The farther a location lies from the umbral path, the smaller that bite becomes. Near the outer edge of the penumbra, the eclipse may be so slight that only careful observation reveals it. Closer to the center, the moon may cover nearly the whole sun, yet a thin crescent of solar surface remains. That narrow crescent is enough to preserve daylight. Even when most of the sun is hidden, the exposed portion is intensely bright. The landscape may dim, but it does not enter the same sudden darkness found inside the umbra. This difference can be surprising. A place just outside the path of totality may experience a very deep partial eclipse, with almost all of the sun concealed, yet the final transformation never arrives. The sky does not open into the corona. The last brilliant edge remains. A small distance on the ground can therefore separate two radically different events. Within the umbra, the sun's surface disappears. Just beyond it, sunlight survives. The boundary moves over Earth as the moon travels in its orbit and the planet rotates beneath it. Its speed across the surface can be immense, often faster than any storm. The exact speed changes along the path because the geometry changes. Near some parts of the track, the shadow races. Near others, it moves more slowly. The width of the umbral path also varies. If the moon appears slightly larger than the sun, the umbra may cover a broader strip. If their apparent sizes are nearly identical, the path becomes narrower and totality shorter. Earth's curvature further shapes where the shadow touches and how long it remains. The result is a dark, moving footprint, often only a small fraction of Earth's width, crossing a globe that turns beneath it. From high above, the umbra appears like a dark patch sliding over clouds and oceans. It does not resemble night spreading from the horizon. It is a localized absence of direct sunlight, surrounded by daylight on all sides. Beneath it, the approach can feel strange because the change does not come evenly. The western sky may darken first if the shadow approaches from that direction. Distant clouds may lose their brightness. The horizon may remain illuminated beyond the shadow, forming a pale or reddish ring around the darkened region. This ring exists because places outside the umbra still receive sunlight. From within totality, the observer stands inside a moving island of darkness while the distant atmosphere remains lit. The penumbra surrounds that island as a wide transition zone. Its light is reduced but not extinguished. The umbra, by contrast, removes the direct solar disk completely. The terms themselves come from Latin words connected with shadow, but their meaning becomes clear through experience. Penumbra suggests almost shadow, the region of partial concealment. Umbra means shadow in its deepest sense. Together they reveal that an eclipse is not simply present or absent. It has degrees. The sun may be uncovered, partly covered, almost covered, or fully covered. Every point on the ground occupies one place within that changing geometry. The same eclipse can therefore appear mild in one region, dramatic in another, and total along a narrow central line. Weather may hide the sky, but it does not change the underlying alignment. Clouds passing through the umbra still lose direct sunlight. Mountains, forests, and cities beneath overcast skies still enter the shadow, even if the black lunar disk cannot be seen. Instruments record the fall in light and temperature. Animals may respond. The event belongs to the whole environment, not only to the clear view overhead. The shadow also reveals the three-dimensional nature of an eclipse. On a flat diagram, the sun, moon, and Earth may seem like circles arranged along a line. In space, their shadows extend as volumes. The umbra is a cone. The penumbra forms a larger surrounding region. These shapes shift continuously as distances and positions change. Earth intersects only part of them. The eclipse seen from the surface is therefore a cross-section through a moving structure in space. A person inside the umbra occupies the narrowest and darkest part of that structure. A person inside the penumbra occupies its widening outer region. Someone beyond both remains in full sunlight, even while another part of the planet is dark. This separation can be measured with great precision. Astronomers calculate the shadow's path using the known motions of the Moon and Earth. the changing distance between them, and the uneven shape of Earth's surface. Modern eclipse maps show the centerline of totality, the northern and southern limits of the umbra, and the broad zones where different percentages of the sun are covered. Yet every line on such a map represents a physical boundary of light moving over real ground. A road may cross from partial eclipse into totality. One hillside may enter the umbra while another nearby remains outside. At the edge, the duration of totality falls towards zero. Deeper inside, it lasts longer. Near the center line, the moon passes most directly across the sun, and the dark interval generally reaches its greatest duration. The shadow has no material substance. It carries no wind of its own and has no surface that can be touched. Still, it changes the world beneath it. Solar heating drops. Brightness collapses, colors lose warmth. The sky reveals stars and planets hidden moments before. The absence of light becomes an event with speed, direction, and shape. The umbra and penumbra make that absence measurable. They divide Earth into regions of full daylight, partial sunlight, and total concealment. As the moon continues forward, those regions sweep onward, leaving ordinary daylight behind. What seems from the ground like the sun being covered is, in a wider view, Earth passing through layers of lunar shadow. The planet does not stop beneath the darkness, it turns through it. The moon does not pause before the sun, it carries the shadow onward. For a few minutes, one narrow path lies beneath the umbra, while a much larger region rests in the penumbra. Then the geometry shifts, the direct light returns, and the shadow moves toward another horizon. The path of totality is the narrow moving corridor where the moon's darker shadow reaches Earth, and the sun's bright surface disappears completely. Outside it, even where the eclipse is deep, some part of the sun remains exposed. Inside it, the last direct sunlight vanishes, and the character of the event changes at once. The path is not a permanent line on the planet. It is traced only while the umbra sweeps across the rotating Earth, touching one region after another before leaving the surface again. Maps show it as a curved band, often crossing oceans and continents, but the band represents something more dynamic than a route. It is the temporary footprint of a shadow moving through space. Its exact position depends on the moon's orbit, Earth's rotation, the changing distance between the bodies, and the curvature of the planet beneath them. Every total solar eclipse draws a different path. Some begin at sunrise, where the shadow first touches Earth at a shallow angle. They cross the globe at great speed, often passing over water for long distances. They end near sunset, where the umbra lifts away from the surface and continues into space. Along this route, totality does not begin everywhere at the same moment. It arrives like a moving threshold. A town may still stand in ordinary daylight while another place farther west has already entered darkness. Minutes later, the shadow reaches the town and then moves onward. The corridor itself may be only tens or hundreds of kilometers wide, small compared with the size of Earth. This narrowness explains why total solar eclipses are uncommon at any particular location. Eclipses occur regularly on the planet, but most pass over places far from any chosen point. The umbra may cross remote seas, polar regions, deserts, or sparsely inhabited land. A city can experience many partial eclipses while waiting centuries for the central shadow. The rarity belongs not to the existence of eclipses, but to the difficulty of placing one location inside the path. The center line of the path usually offers the longest totality because the moon crosses most directly in front of the sun there. Near the northern or southern limits, the lunar disk barely covers the solar disk completely. Totality becomes shorter, sometimes lasting only a few moments. At the exact edge, The geometry is finely balanced. Lunar mountains and valleys can cause sunlight to break through in separate points, producing an uneven boundary between total and partial eclipse. A short journey toward the center can add precious seconds or minutes of darkness. A short journey outward can remove totality entirely. This sharp difference is one of the eclipse's most striking features. A place beneath almost all of the moon's apparent disk may still remain outside the umbra. The sun can be more than 99% covered. Yet the surviving sliver continues to flood the landscape with light. The world may dim. The air may cool, and shadows may become strange, but the corona does not fully emerge. Only when the final bright fragment disappears does totality begin. The path therefore marks not merely a difference in degree, but a threshold between two distinct states of the sky. Calculating that path requires a detailed understanding of motion and shape. The moon's orbit is not a perfect circle, and its speed changes as its distance from Earth changes. Earth's orbit around the sun also varies slightly, altering the sun's apparent size. The planet rotates beneath the moving shadow, carrying locations eastward while the umbra travels across the surface. Earth is not a perfect sphere, and its mountains and elevations affect the precise timing at the edges. The moon itself has an irregular surface, so the outline of its shadow contains the imprint of lunar topography. Modern predictions include these factors, allowing astronomers to estimate when totality begins and ends for specific locations, often with remarkable precision. Yet a map can make the path seem simpler than the experience. On paper, it is a band with clear limits. On the ground, it is transformation unfolding through light, temperature, colour, and motion. Long before totality, the partial phase begins. The moon slowly covers the sun, but the day may remain deceptively bright. As the eclipse deepens, the quality of light changes. Shadows sharpen because the visible solar source narrows. Small gaps between leaves project crescent images onto walls and ground. The air cools as less solar energy reaches the surface. Near the final minutes, the landscape may take on a muted tone, as though brightness is being drained without the warmth of sunset. The horizon can remain luminous because regions beyond the umbra still lie in sunlight. The approaching shadow may appear as a darkening mass across distant sky or land, especially from a high place with a wide view. Then the final edge of the sun collapses into beads and a brilliant point. The umbra arrives. Totality within the path is brief because the shadow never stops moving. Its speed varies, but it can cross the ground faster than sound. The moon's orbital motion drives the shadow generally from west to east, while Earth's rotation modifies its course and speed. The path often curves across maps because it lies on a spherical, rotating surface. Near the beginning and end of an eclipse, the shadow strikes Earth obliquely, stretching its footprint. Near the middle, it may fall more directly, creating different widths and durations. The longest possible totality occurs when several conditions favour it. At once the moon is relatively close to Earth, and therefore appears larger. Earth is relatively far from the sun, and the solar disk appears smaller. And the shadow passes near the equatorial region where its motion across the ground can be slower, even under such conditions. Totality lasts only minutes. The path may extend across thousands of kilometres, but each point remains in darkness for only a short interval. Clouds add uncertainty without changing the geometry. The umbra reaches the surface whether the sky is clear or overcast. Under thick cloud, the sun may remain invisible throughout the eclipse, but the sudden darkening still arrives. The atmosphere dims, birds may quiet, artificial lights may switch on, and the environment enters the central shadow. Clear skies reveal the full structure of the event, but cloud cannot prevent totality. It can only conceal the view above. This makes the path both predictable and fragile. Its route is known years in advance, yet the human experience at any one place depends on local weather at the exact time the shadow passes. For this reason, observers often travel within the path, choosing locations with favourable climate and open horizons. Their movement across Earth mirrors the precision of the celestial alignment. To see totality, a person must not only live at the correct era in the history of the Earth-Moon system, but also stand in the correct corridor on the correct day beneath a clear enough sky. From space, the path becomes easier to understand. The moon casts a long shadow away from the sun. Earth moves through that shadow while turning. The intersection between the umbral cone and the curved planetary surface forms a dark oval that slides across the globe. The line followed by the centre of that oval becomes the centre line of totality. The broader region touched by it becomes the path. Nothing is carved into Earth, yet the shadow leaves a route that can be predicted before it arrives and reconstructed after it is gone. Across that route, millions of separate landscapes share the same temporary loss of the sun. Mountains enter darkness, then return to light. Rivers reflect a blackened sky. Cities pause under the corona. Ships at sea pass through a night only a few minutes wide. The path links these places without regard for borders or terrain. It follows geometry alone. Its beginning and end may lie in empty ocean, while its middle crosses crowded land. It may pass over ancient structures, forests, ice, or desert, but none of these features can bend it. The shadow belongs to the alignment of worlds. The path of totality is therefore both a location and a moment. It cannot be visited after the eclipse has passed, even though the ground remains. The same field, road, or coastline returns immediately to ordinary daylight. What made it part of the path was not the place itself, but the brief arrival of the umbra. For a few minutes, that narrow band becomes the only region on Earth where the sun is completely hidden. Beyond its edges, the day continues in partial light. Ahead of it, totality has not yet begun. Behind it, totality is already memory. The path moves onward as a silent boundary, carrying darkness across a bright planet and revealing how exact a shadow must be to turn midday into night. Partial and annular eclipses begin with the same three bodies and the same basic alignment, yet they reveal how sensitive the sky is to small changes in position and distance. In a partial eclipse, the moon crosses only part of the sun from a given location. In an annular eclipse, it passes directly across the centre but appears too small to cover the solar disk completely. One event leaves a bright crescent, the other leaves a complete ring. Neither produces totality, though both can darken the day and expose the precision of the moving geometry. A partial eclipse is the most common solar eclipse experience because the moon's penumbral shadow covers a much wider region than its central shadow. Within that broad zone, the observer sees the lunar disk overlap the sun without fully hiding it. The amount of coverage depends on position. Near the outer edge of the penumbra, the moon may remove only a small arc from the sun, farther inward. The overlap grows until the sun becomes a narrow crescent. The same eclipse can therefore appear modest in one place and nearly total in another. The difference comes from the observer standing at a different angle beneath the shadow. Each location sees the moon projected against a slightly different part of the sun. This changing viewpoint is called parallax, the apparent shift of a nearby object against a distant background when seen from different positions. The moon is close enough for this effect to matter across the width of Earth. From one region, it may appear to pass across the upper half of the sun. From another, it may cross the lower half. Only within a central corridor does the alignment become direct. Outside that corridor, the eclipse remains partial. Even a very deep partial eclipse is not the same as totality. A thin exposed segment of the sun can remain painfully bright. Human eyes adjust to the general dimming of the landscape, making the surviving sunlight especially dangerous because the instinct to look upward grows as the world becomes strange. The sun does not become safe simply because most of it is covered. Every visible part of its surface continues to emit intense light. The difference between total and partial eclipse may be only a slender arc in the sky, but that arc preserves direct sunlight and keeps the corona hidden. The atmosphere does not become as dark, bright stars are less likely to appear, and the sudden transformation associated with the umbra never fully arrives. The event approaches a threshold but does not cross it. Annular eclipses are different. They occur within the moon's antumbral shadow, beyond the point where the umbral cone ends. The sun, moon, and observer are closely aligned, but the moon is too far from Earth to appear large enough to cover the sun. Instead, the lunar disk sits inside the solar disk, leaving a bright ring around its edge. The effect is sometimes called a ring of fire, though the ring is not actual fire encircling the moon. It is the exposed surface of the sun, visible all around the dark lunar silhouette. The brightness belongs entirely to the distant star behind it. The reason the moon appears too small is its elliptical orbit. Its distance from Earth changes continuously. Near the farthest part of its orbit, it looks slightly smaller in the sky. If a central solar eclipse occurs then, the moon may fail to cover the sun even though it passes directly in front of it. The sun's apparent size also matters. Earth's own elliptical orbit changes its distance from the sun through the year. When Earth is closer to the sun, the solar disk appears slightly larger, making complete coverage more difficult. Annularity results from the balance of both distances: a smaller apparent moon, a larger apparent sun, or a combination of the two can preserve the ring. The difference between an annular and total eclipse may depend on a narrow margin, too small to judge without careful measurement before the event. Yet the outcome across the landscape is unmistakable. During annularity, daylight weakens but does not vanish. The ring remains an intense source of light. Shadows may sharpen and colours may cool, but the sky does not reveal the full corona because the exposed solar surface overwhelms it. The central shadow passes, yet it carries no complete night. The moon seems perfectly centered and still insufficient. This can make an annular eclipse feel like an alignment that reaches exact position, but not exact scale. The geometry is correct in direction, but the apparent sizes do not match. As the moon moves across the sun, the ring does not appear immediately. The eclipse begins as a partial phase, with the dark lunar edge entering the solar disk. The overlap grows until the moon is surrounded by sunlight. For a brief interval, annularity is achieved, then the moon continues onward, the ring breaks, and the eclipse returns to a partial phase. Near the beginning and end of annularity, irregular features along the moon's edge can allow sunlight to appear in beads. Because the moon's surface is marked by mountains, craters, and valleys, its silhouette is not perfectly smooth. These features shape the thin line of sunlight and can create a broken ring for a few moments. The event may resemble the approach to totality, but sunlight never disappears all around the moon at once. The annular path, like the path of totality, is narrow. Observers outside it see a partial eclipse. Even if they are close to the center, this creates a layered experience across the planet. A person within the antumbra sees a ring. Someone farther away sees a crescent. Someone beyond the penumbra sees an ordinary sun. All three views occur at the same time, produced by different positions beneath one moving shadow. The eclipse has no single appearance for Earth as a whole. Its form depends on where the line of sight passes through the geometry. Partial eclipses can also occur when the central shadow misses Earth entirely. The new moon may pass near a node but not close enough for the umbra and tumbra to touch the planet. Only the penumbra reaches the surface, often across high northern or southern latitudes. In such cases, no location experiences totality or annularity. The entire event is partial. From space, the outer shadow brushes the edge of Earth rather than crossing it centrally. From the ground, the sun loses a portion of its disk and then slowly regains it. The eclipse may seem less dramatic than a total one, but it still reveals the moon's otherwise invisible daytime passage. It shows that the lunar orbit has come close to the necessary line without fully meeting it. The shape of a partial eclipse also changes with time. At first contact, the moon touches the apparent edge of the sun. The dark indentation grows as the two disks overlap. Maximum eclipse occurs when the overlap is greatest for that location. Then the moon moves away, returning the sun to a complete circle. The process may last for hours, much longer than the central phase of a total or annular eclipse. Because the change is slow, it becomes a study in motion that is usually too gradual to notice elsewhere in the sky. The moon appears to move about its own width against the stars in roughly an hour, and the eclipse makes that movement visible against the brilliant solar background. With safe projection, the shifting curve can be followed as one world crosses another. Small openings between leaves act as natural pinhole projectors, casting repeated images of the eclipsed sun onto the ground. During a partial eclipse, these images become crescents. During annularity, they can become tiny rings near the central phase. The ground fills with copies of the sky, each shaped by the remaining sunlight. An event occurring hundreds of thousands of kilometers away appears beneath trees and along walls, translated into patterns of light. Partial and annular eclipses therefore belong to the same family of alignment as totality, but they reveal different limits within it. The partial eclipse shows what happens when direction is incomplete. The annular eclipse shows what happens when direction is exact, but apparent size is insufficient. In one, the moon misses the center. In the other, it reaches the center but cannot cover the whole sun. Both demonstrate that an eclipse is not a simple switch between light and darkness. It is a continuum shaped by angles, distances, orbital tilt, and the observer's place on a curved world. A shift of position changes a ring into a crescent. A shift of distance changes a ring into total darkness. The same celestial bodies continue along the same paths, but the sky presents a different form each time, through these variations. The eclipse reveals how little the geometry must change for the entire character of daylight to change with it. A hybrid solar eclipse is the rarest expression of an already rare alignment, a single event that changes its form as the moon's shadow travels across the curved surface of Earth. Along one part of the path, the moon appears slightly too small to cover the sun, leaving a narrow ring of light. Farther along, the same eclipse becomes total, and the solar surface disappears completely. Later, it may return to annularity before the shadow leaves the planet. Nothing abrupt happens to the moon, and the sun does not change size in any sudden way. The transformation comes from the changing distance between the observer and the moon as Earth curves beneath the moving shadow. A difference measured across the radius of a planet becomes enough to decide whether the final rim of sunlight survives. The balance is so fine that the geometry seems to rest on an edge. In most central solar eclipses, the shadow has a single character along the main path. If the moon appears large enough, the umbra reaches Earth and totality follows. If it appears too small, the umbral cone ends above the surface, and the antumbra produces an annular eclipse. In a hybrid eclipse, the tip of the umbra lies extremely close to Earth. The planet's surface is not flat, so some regions stand slightly nearer to the moon than others because they lie on the curved middle of the globe beneath the shadow. Near the beginning of the eclipse, the shadow often reaches Earth at a shallow angle close to sunrise. The surface there may sit just beyond the end of the umbral cone, placing observers in the antumbra and leaving a bright ring around the moon. As the shadow moves toward the central part of Earth's visible disk, the surface rises toward it along the planet's curvature. The ground becomes close enough for the true umbra to touch. The ring closes. Totality begins. Farther along, as the shadow approaches sunset and Earth curves away again, the umbra may lift from the surface, restoring annularity. The exact sequence depends on the distances and angles of that eclipse. The term hybrid reflects this shifting identity. It does not mean that one observer sees an eclipse changing repeatedly from annular to total while remaining in a single place. Each location usually experiences only one central form because the shadow passes quickly. The hybrid nature appears across the full path. One region sees a ring, another, farther along the track, sees the sun vanish. Both observations belong to the same uninterrupted alignment. The difference is created by position on Earth rather than by a major change in the moon's orbit during those few hours. This makes a hybrid eclipse a planetary event in a particularly clear sense. Earth's shape becomes an active part of what the sky reveals. The distinction between total and annular eclipse can depend on only a small apparent difference between the widths of the moon and sun. Their disks already match closely, and during a hybrid event that match becomes almost exact. The moon may appear larger than the sun by only a tiny amount at some points, and smaller by a tiny amount at others. The edge of the moon therefore passes very close to the edge of the sun. Near totality, the duration can be brief because the lunar disk has little extra width with which to cover the solar disk. The umbral path may also be narrow. Observers near its limits may see sunlight break through lunar valleys for much of the central phase, while those nearer the centre experience a short but complete concealment. The corona emerges, but the black disk may seem barely large enough to hold back the photosphere, the brilliant visible layer of the sun. At annular locations, the remaining ring may be extremely thin, giving the appearance of an eclipse only a breath away from totality, yet the difference remains decisive. Any exposed part of the solar surface preserves intense direct light and prevents the sky from reaching the same darkness found under the umbra. The corona remains overwhelmed. The landscape dims but does not fully enter the central night. A narrow luminous circle continues around the moon, proving that the umbral cone has ended just above the ground. From only a modest change in location along the path, that ring can disappear. The ground has moved close enough to meet the shadow before it narrows to a point. The geometry is delicate, but it is not unpredictable. Astronomers calculate hybrid eclipses by tracing the changing shape and position of the lunar shadow against a rotating, curved Earth. The moon's distance must be known, as must the sun's apparent size, the orientation of the orbital planes, the speed of the shadow, and the shape of the planet. Even the fact that Earth is slightly wider around the equator than from pole to pole can influence exact contact times and path boundaries. Elevation matters near the most sensitive edges. A mountain stands closer to the moon than nearby sea level, though only by a tiny fraction of the total distance. During an eclipse with comfortable margins, that difference does not change the central type. During an alignment balance near the limit, small differences become important. Lunar topography adds another layer. The moon's outline is formed by mountains, crater rims, and valleys. When the apparent sizes of sun and moon are nearly identical, these features control where sunlight remains visible. At the beginning or end of a very short totality, bright points may persist between lunar mountains. Along the edge of the central path, some observers may see a broken sequence of light rather than a smoothly vanishing solar surface. Hybrid eclipses are uncommon because several conditions must coincide. The new moon must pass close enough to an orbital node for a central eclipse. Its apparent size must be nearly equal to that of the Sun, placing the tip of the umbral cone close to Earth. The shadow must then cross the curved planet in a way that allows the surface to move into and out of the cone. If the moon appears even slightly larger, the umbra reaches Earth along the entire central path, and the eclipse is total. If it appears slightly smaller, the umbra falls short everywhere, and the eclipse is annular. Only within the narrow middle range can both forms occur during one event. Their paths can cross remote ocean for much of their length, limiting the number of people who witness the transition in type. A ship near one section may see annularity, while an island farther along experiences totality. The event links these separate views into one moving structure that no single location can fully observe. From space, the shadow does not carry labels such as total or annular. It is a cone whose tip approaches, touches, and withdraws from a curved surface. The names describe how that encounter appears from below. The hybrid eclipse also exposes the limits of simple diagrams. Textbook images often show the Sun, Moon, and Earth along a straight line, with a neat cone of shadow reaching toward the planet. Such drawings explain the basic arrangement, but they flatten a system that is always moving. The Moon advances in its orbit, Earth rotates, the distance between the bodies changes. The shadow strikes the surface at changing angles. The planet curves toward and away from the cone. A hybrid eclipse occurs because all these details matter at once. The central line may be nearly perfect, but perfection in direction does not guarantee one unchanging result. Scale and surface shape complete the event. The transition from ring to totality carries a quiet implication. The eclipse is not only an image formed in the sky, it is a relationship between the sky and the ground. The same moon and sun can produce different realities at different places because Earth is part of the optical system. Its curvature changes the observer's distance from the moon. Its rotation carries landscapes through distinct regions of shadow. The planet does not merely receive the eclipse, it helps determine its visible form. During a hybrid event, that role becomes impossible to ignore. A ring survives at one horizon because the surface lies slightly too far from the moon. Farther along, the planet curves into the umbra, and the ring closes. The sun disappears. Still farther on, the surface falls away and the ring returns, across a world thousands of kilometers wide. The difference is small, but the sky changes completely. The hybrid eclipse rests at the boundary between two kinds of darkness, revealing how a planetary curve can decide whether daylight is reduced to a circle or removed altogether. The final moments before totality do not arrive as a simple fading of light. They unfold through a sequence of increasingly delicate changes along the edge of the moon, where mountains, crater walls, and low valleys briefly shape the last surviving sunlight. From a distance, the moon appears as a smooth black circle. Its true horizon is rugged. Peaks rise above ancient plains, and depressions cut into the airless surface. As the lunar disk advances across the sun, these uneven features become important. Sunlight disappears first behind the higher ground. It continues to pass through the lower gaps. The shrinking solar crescent breaks into separate points of brilliance, each one shining through a valley along the moon's edge. These points are known as Baily's beads. They are not objects floating near the moon, and they are not eruptions from the sun. They are fragments of the solar surface seen through the lunar landscape in silhouette. Their appearance reveals the moon as a world rather than a perfect geometric disk. The edge that seems smooth to ordinary sight becomes a distant chain of mountains and hollows controlling the final pattern of day. Baily's beads may appear shortly before totality, and again just after it ends. Before totality, they vanish one after another as the moon moves farther across the sun. After totality, the process reverses. Bright points emerge through valleys on the opposite edge, announcing the return of direct sunlight. The sequence is brief, often lasting only seconds, yet it compresses several scales into one view. The sun lies enormously far beyond the moon. The valleys belong to terrain hundreds of thousands of kilometers away. Their shadows and openings determine which parts of a distant star remain visible from one narrow region on Earth. The beads therefore mark the meeting of solar light, lunar topography, and the observer's exact position inside the moving shadow. A person several kilometers away may see a slightly different sequence because the line of sight crosses a different part of the moon's edge. Near the boundary of totality, the beads can persist longer, appearing as a broken chain of light around portions of the lunar disk. Near the center of the path, they usually disappear more quickly as the moon covers the sun more completely. Their timing is predictable because the shape of the moon's limb, the visible outer edge of its disk, can be mapped. Lunar mountains and valleys are measured by spacecraft and by repeated observation. Astronomers can model where sunlight will pass through the lowest regions and where high terrain will block it. What once appears as a flickering irregularity becomes a readable signature of the lunar surface. Each bead has a geographic cause on the moon, though the feature itself remains invisible in the glare. The final bead often grows more isolated as the others disappear. It shines beside the dark lunar disk while the faint inner corona begins to emerge around the moon. This combination creates the effect known as the diamond ring. The remaining point of sunlight forms the diamond, while the corona forms a pale circular band around the black center. The name describes the appearance, but the phenomenon is still a matter of geometry. The last exposed region of the photosphere, the sun's brilliant visible surface, sends direct light toward the observer through a lunar valley. Around it, the much fainter corona becomes partly visible because almost all of the photosphere is already covered. For a moment, the bright point and the soft outer atmosphere appear together. Then the moon moves slightly farther. The valley no longer opens onto the solar surface. The diamond vanishes and totality begins. The change can be startling because the photosphere is vastly brighter than the corona. Even a tiny exposed part of the sun dominates the sky. When that last part disappears, the balance of visible light changes immediately. The corona, present all along but hidden in glare, becomes clear. The sky darkens sharply. The black disk of the moon seems to detach from the surrounding brightness, and the central eclipse takes on its complete form. The disappearance of the diamond ring is therefore not only a visual marker, it is the boundary between direct sunlight and its full obstruction. Before that moment, the eye still receives intense rays from the solar surface. After it, within the umbra, the photosphere is concealed. This boundary is also why eclipse safety depends on precise timing. During all partial phases, including the appearance of Baily's beads and the diamond ring, direct solar light remains visible and proper eye protection is necessary. Ordinary sunglasses do not reduce the light enough. Safe eclipse viewers use filters designed to block the overwhelming majority of visible ultraviolet. An infrared solar radiation, indirect projection, offers another method by allowing an image of the sun to fall onto a surface rather than entering the eye directly. Only during complete totality, when no part of the photosphere is visible, can the eclipsed sun be viewed without the filter. The safe interval ends as soon as the first bright bead returns. The timing can differ from one location to another, especially near the edge of the path, so the visible sun itself remains the decisive signal. Any exposed photosphere means direct sunlight has returned. The beauty of the final moments comes partly from their speed. For much of the partial phase, the moon appears to cross the sun slowly. The event may continue for more than an hour before totality, and the changes in daylight can be gradual. Near the end, however, the visible solar crescent becomes extremely thin. A small motion of the moon then removes a large fraction of the remaining light. The sequence accelerates in appearance. The crescent contracts, its tips shorten, it fractures into beads, one bright point survives. Then it is gone. The long approach resolves into a few seconds of rapid transformation. The environment responds at the same time. Shadows become unusually sharp and faint. The last sunlight may produce narrow bands of illumination across the ground. The sky deepens in colour. The horizon remains brighter beyond the umbra, while the region overhead darkens. Air temperature may continue to fall. Birds and insects may change their behaviour as the usual signals of day weaken. Yet the most exact countdown is taking place along the moon's edge, where each disappearing bead records the closing of another lunar valley against the sun. The ruggedness of the moon also prevents the beginning of totality from being perfectly uniform around the disk. In an ideal system with a smooth spherical moon, the last solar arc would shrink in a clean and continuous way. The real moon interrupts that simplicity. One valley remains open after another is closed. A peak may block a segment early. A deep depression may preserve a bead for a moment longer. This uneven sequence gives the eclipse a texture created by geology. The mountains involved are ancient, formed by impacts and volcanic processes across immense spans of lunar history. Their present shapes become visible indirectly because they alter the passage of sunlight, a landscape with no weather. Oceans, or living observers, casts its profile onto Earth during the final seconds before darkness. The beads carry traces of that history without revealing any surface detail directly. They show only where the moon is high and where it is low. The diamond ring brings those fragments into a single final point. Its brilliance can seem disproportionate to its size because the sun's surface remains intense, even when almost completely hidden. The human eye and cameras can register dramatic rays and glare around the point. But the actual exposed region is narrow. This contrast between tiny source and overwhelming brightness reinforces the central lesson of totality. Almost complete coverage is not complete coverage. The final point matters. Until it disappears, the corona cannot fully dominate and the world does not enter the deepest part of the shadow. Once it vanishes, the transformation is immediate. Totality does not slowly blend into existence. It begins when the last direct ray from the photosphere is cut off along that line of sight. This same sequence returns in reverse at the end. A point of light appears suddenly on the opposite edge. It expands into a diamond ring. More beads emerge as lunar valleys uncover the sun. The corona fades back into glare. The sky brightens with remarkable speed. The central darkness ends, though most of the sun may still remain hidden. The eclipse continues as a partial event, but its most fragile interval has passed in this way. Baily's beads and the diamond ring act as gates on either side of totality. They are brief, precise, and shaped by terrain on another world. They turn the moon's unseen mountains into markers of time. One bead after another disappears, and daylight is reduced to a final point. When that point closes, the alignment reaches its most complete expression, and the shadow becomes whole. Totality begins when the last exposed point of the sun's visible surface disappears behind the moon. The change is immediate. The glare that has dominated the sky collapses, and the black disk of the moon stands where the sun had been. Around it, a pale and delicate atmosphere becomes visible, extending outward in streamers, loops, and soft rays. This is the solar corona, the outermost region of the sun's atmosphere. It is always present, but under ordinary daylight it is hidden by the brightness of the photosphere, the luminous surface seen from Earth. During totality, the moon blocks that overwhelming light while leaving the surrounding corona exposed. The eclipse, therefore, does more than remove the sun. It reveals a part of the sun that is usually invisible. The corona does not have one fixed shape. It is guided by the sun's magnetic field, which changes across the solar cycle. At some times, long streamers stretch outward from the equatorial regions. At others, the corona appears more evenly spread around the hidden disk. Bright loops may arch above active regions, while faint structures extend far into space. The light is soft compared with the photosphere, yet against the darkened sky it becomes clear. Its appearance can seem almost motionless during the few minutes of totality, though the plasma within it is hot, dynamic, and constantly flowing. The corona reaches temperatures far higher than the visible surface below, a fact that remains one of the long-standing puzzles of solar physics. Magnetic processes are understood to carry and release energy there, but the details of coronal heating continue to be studied. Totality allows the eye to see the result of that hidden activity as a quiet white atmosphere surrounding a black center. Near the edge of the moon, other features may briefly appear. Thin arcs of reddish light can mark the chromosphere, a lower layer of the solar atmosphere above the photosphere. Prominences, which are large structures of glowing plasma held by magnetic fields, may extend beyond the moon's silhouette. Their color comes from hydrogen emitting light at specific wavelengths. To unaided sight, they may appear as small pink or red points along the edge. They are not flames in the ordinary sense. The sun has no solid surface and no air in which fire burns. These structures are made of electrically charged gas shaped by magnetism and heated by solar energy. The moon's dark outline makes them visible by removing the much brighter background. The center of the eclipse remains completely black because the night side of the moon faces Earth. No sunlight illuminates the lunar surface directly from this angle. Earthshine, the faint sunlight reflected from Earth onto the moon, is too weak to reveal detail against the surrounding corona. The moon becomes a silhouette, and its familiar craters and plains disappear. The object that shines at night as a silver disk is transformed into a perfect absence of light. This darkness is not an empty hole in the sky. It is the solid body of the moon, moving silently between Earth and the sun. Its apparent stillness during totality is deceptive. The moon continues along its orbit, the shadow continues across Earth, and the alignment is already beginning to loosen. The black disk is a moving world, and the darkness lasts only because its path briefly matches the observer's line of sight. The sky around it may deepen to a dark blue or violet rather than becoming completely black. The exact appearance depends on atmospheric conditions, the length of totality, and the width of the umbral shadow. Bright planets can emerge, and the strongest stars may become visible. They have not suddenly brightened. They were present in the daylight sky all along, hidden by scattered sunlight in Earth's atmosphere as the direct light weakens. The background sky darkens enough for them to appear. This creates a rare view in which day and night overlap. The sun remains above the horizon, but its surface is covered. The stars return, though only briefly. Around the horizon, a band of warm colour often remains. This glow comes from regions outside the umbra, where sunlight still reaches the atmosphere. From inside totality, those distant areas lie beyond the central shadow and remain in partial light. The horizon can therefore appear like sunset in every direction, while the sky overhead is dark. The effect reveals the limited size of the umbra. The observer stands within a moving patch of night surrounded by day. The horizon marks the border between the darkened region and the illuminated world beyond it. Unlike an ordinary sunset, the glow does not belong to one direction. It can encircle the landscape because sunlight continues around the entire edge of the shadow. The ground changes as sharply as the sky. Colours lose their normal warmth, and the land may take on a muted silvery tone. Artificial lights may switch on automatically. Shadows become faint or disappear because the direct solar source is gone, though the corona and horizon still provide some illumination. The temperature may fall further as the surface continues to lose heat. The air can feel still, or local winds may shift as the pattern of heating changes. These effects vary with weather and terrain, but the central sensation is consistent. The environment enters a brief interval that resembles night without becoming true night. The planet has not turned away from the sun. Instead, the moon has placed a small moving barrier in the path of daylight. Totality is usually short because the moon's umbral shadow is narrow and fast. At one location, it may last only seconds or a few minutes. Even the longest possible total solar eclipses remain brief compared with the hours of partial phases surrounding them. This short duration gives the central darkness a compressed quality. Features appear almost all at once: the corona, planets, stars, horizon glow, changing temperature, and the black moon. There is little time for the scene to become familiar. Before the eyes fully adjust, the geometry begins to open again. The eclipse is most complete at the moment when the moon's centre passes closest to the centre of the sun. This is the middle of totality for that location. Yet the word complete does not mean motionless. Every instant differs slightly from the one before. The corona remains visible, but the moon continues eastward across the solar disk. The hidden photosphere approaches the opposite lunar edge. The shadow moves onward across Earth, carrying its deepest point toward another region. Totality is therefore not a pause in celestial motion. It is a narrow interval created by motion itself. Scientific observations during totality have long taken advantage of this natural concealment. Before instruments in space could block the sun with artificial disks, eclipses offered rare chances to study the corona, measure its structure, and examine light passing near the sun. Modern observatories can observe much of the solar atmosphere every day. Yet total eclipses still provide valuable views of regions close to the solar edge and allow instruments to combine wide detail with the moon's precise natural cover. The eclipse also remains a test of prediction. Its timing, duration, and path can be calculated in advance, while observations refine knowledge of the moon's motion, Earth's rotation, and the solar atmosphere. The event may feel ancient and mysterious, but it is also a working laboratory created by alignment. Inside totality, the difference between knowledge and experience becomes especially clear. The mechanics can be understood completely enough to predict the event, yet the sight remains strange. A star becomes a black circle. Its hidden atmosphere appears like a pale crown. Night gathers overhead while daylight survives around the horizon. The moon, normally seen by reflected sunlight, becomes an invisible world defined only by the light it blocks. The ordinary brightness of the sky is revealed as a thin condition, dependent on an unobstructed line between one place on Earth and the solar surface. When that line closes, the deeper architecture of the scene emerges. The sun is no longer only a bright disk. It becomes a layered atmosphere, a magnetic environment, and a source of light extending far beyond the visible edge. The moon is no longer only a night object. It becomes a moving mask with a shadow large enough to cross a planet. Earth is no longer simply beneath daylight, it stands within a narrow cone in space. These truths are always present, but totality makes them visible together. Then, near the end, the corona begins to lose its dominance along one side. A bright point is about to return through a lunar valley. The black disk still covers the sun, but the alignment has already started to break. Totality remains complete for only a few final moments. The horizon stays bright. The corona surrounds the moon. The shadow continues eastward. Then direct sunlight returns, and the hidden atmosphere vanishes once more into glare. Life responds to a total solar eclipse not because animals and plants understand the alignment above them, but because many living systems are tuned to light, temperature, and the daily rhythm of sunrise and sunset. When the moon's shadow removes daylight in the middle of the day, those signals change abruptly. Birds may grow quiet. Insects associated with evening may begin to call. Flowers may start to close. Grazing animals may pause, seek shelter, or behave as though night is approaching. Yet the event offers a rare natural experiment, a short, predictable disruption of daylight that moves across whole ecosystems. The eclipse does not stop biological clocks, but it can confuse the cues that normally guide them. Many organisms live by circadian rhythms, internal cycles that repeat roughly every day. These rhythms influence sleep, feeding, migration, hormone release, leaf movement, and many other processes. They are generated within the body, but they are adjusted by environmental signals, especially light. Dawn and dusk help keep the internal cycle aligned with the rotation of Earth. A solar eclipse is too brief to reset that clock completely, but it can trigger behaviors that depend on immediate brightness. A songbird does not need to believe that night has arrived. Its nervous system only needs to register a sudden decline in light, similar to the decline that usually accompanies evening. The result may be silence, movement toward a roost, or a change in calling. Other birds may become more active, especially species that normally begin feeding near dusk. Their response can begin during the deep partial phase before totality, because the environment has already grown dimmer and cooler. Insects often provide some of the clearest signs. Crickets and katydids may begin their evening chorus as the light falls. Cicadas that depend on warmth and daylight may quiet. Bees may return toward their hives or reduce foraging. Moths may become active, while day-flying butterflies settle. Many insects respond quickly to small variations in brightness and temperature. A total eclipse alters both at once. The air cools, shadows sharpen, and the spectral quality of light changes as the remaining solar crescent narrows. To an insect whose behavior is guided by simple environmental thresholds, the event may resemble a compressed sunset. Then, only minutes later, light returns with the speed of an unexpected dawn. The organism must reverse course almost immediately. Birds can show similarly complex reactions. Some flocks may head toward nighttime resting places. Water birds may move toward shore. Roosters may crow when the sun returns, responding as though morning has begun again. Nocturnal birds may call briefly during totality, while daytime species become still. Yet other observations find little response at all. A bird occupied with feeding or nesting may continue despite the dimming. A species living under forest cover may already experience rapid changes in light as clouds and leaves shift overhead, making the eclipse less unusual. The eclipse is not a command sent to nature. It is a sudden change in information, and each organism interprets that information through its own senses and habits. Mammals may also react, though their behavior is often harder to observe across large areas. Domestic animals sometimes return toward barns, resting places, or familiar evening locations. Cattle may stop grazing. Horses may become alert, dogs may show little concern or may respond to changes in human activity rather than to the sky itself. Wild mammals that are active at dawn or dusk may begin to move, while strictly daytime animals may settle. Nocturnal species rarely have enough time to enter a full night cycle before daylight returns. Their activity, if it begins, is interrupted almost as soon as it starts. The brevity of totality is therefore important. The eclipse can trigger the opening steps of a nighttime routine without allowing the routine to develop. It is a false evening followed by an immediate morning. Plants respond more slowly than many animals, but some changes can still be visible. Certain flowers close when light fades, protecting pollen or reducing heat loss. Leaves in some species shift position according to daily rhythms. During a deep eclipse, flowers may begin to fold inward, and leaves may droop or rise depending on the plant. Photosynthesis, the process by which plants use light to build chemical energy, declines as sunlight disappears. The change is immediate at the cellular level because the supply of light has fallen. Though the eclipse is too short to cause lasting harm, stomata, the tiny openings through which leaves exchange gases and water vapor, may begin to respond to cooling and darkness. Soil and leaf temperatures drop. The local flow of carbon dioxide and moisture changes briefly. These responses are often subtle, but instruments can measure them even when the plant appears still. The eclipse passes across ecosystems as a wave of reduced energy. A forest canopy receives less sunlight. The ground beneath it cools. Air movement within the vegetation can change as temperature differences weaken. In open grassland, the fall in surface heating may be more direct. Over water, the reflection of the sky darkens, and aquatic animals may respond to the altered light above. Zooplankton in lakes and oceans often move vertically according to day and night, descending during daylight and rising after dark. An eclipse may influence this movement, though the response depends on depth, water clarity, and the duration of darkness. Fish may change feeding or swimming behavior. Coral reef organisms that follow light cycles may show brief shifts. The moon's shadow therefore reaches beyond the land. It enters water as a dimming signal. Fading with depth but still altering the upper layers, human environments add another layer of change. Streetlights may switch on, buildings may illuminate automatically, traffic patterns may shift as people stop to watch. Animals living near cities can react to both the natural eclipse and the sudden behavior of humans around them. A dog may become anxious because crowds cheer. Birds may be disturbed by movement and noise at the moment they would otherwise become quiet. Scientific observations must account for these influences. The eclipse is a natural experiment, but it rarely occurs in a world untouched by human presence. Researchers may use acoustic recorders, motion sensors, temperature gauges, and light meters to separate biological responses from anecdote. Large citizen science projects can also gather observations across the path. The reports require careful interpretation because expectation can shape what people notice. A single quiet bird or chirping cricket does not prove a broad rule. Patterns emerge only through repeated measurements across species and locations. Total solar eclipses are valuable for such study because their timing and path are known in advance. Instruments can be placed before the shadow arrives. Normal behavior can be recorded, followed by the partial phase, totality, and the return of sunlight. The same site then serves as its own comparison across a rapidly changing interval. Even so, no two eclipses occur under identical biological conditions. One may cross a spring forest during nesting season. Another may pass over winter grassland, tropical ocean, desert, or city. Time of day matters. An eclipse near morning or evening may blend with ordinary daily transitions, while one near midday creates a sharper disruption. Cloud cover can weaken the contrast. Temperature change depends on local weather and surface conditions. The living response is therefore as varied as the path itself. What remains consistent is the dependence of life on predictable solar energy. The eclipse reveals that dependence by removing the signal briefly. Day-active animals rely on light not only to see, but to organize time. Plants use it as both fuel and information. Insects follow it through thresholds of brightness and warmth. Entire communities move within rhythms created by Earth's rotation beneath the sun. Totality interrupts those rhythms without changing their source. The planet continues turning. The sun continues shining. The moon only blocks one narrow path. Yet within that path, the ordinary contract between life and daylight is suspended. Evening behaviors begin at the wrong hour. Night voices rise and fall within minutes. Flowers respond to darkness that cannot last. Then the first bead of sunlight returns. The sky brightens, and the false night dissolves. Birds resume calling. Insects quiet or change their chorus. Animals that began moving toward rest may stop and return. Plants reopen more slowly. The ecosystem absorbs the interruption and continues. No lasting night has arrived, but for a brief interval, the living surface of Earth responds to a shadow from space. A solar eclipse changes the appearance of the sun, but it does not make ordinary sunlight harmless. During every partial phase, including the long approach to totality and the return of the sun afterward, the exposed solar surface remains bright enough to injure the eye. The danger can be easy to underestimate because the landscape grows dimmer and the sun appears smaller. A thin crescent may seem less threatening than a full disk, yet the remaining light still comes directly from the photosphere, the brilliant visible surface of the sun. Looking at it without proper protection can damage the light-sensitive retina at the back of the eye. The injury may occur without immediate pain because the retina has no pain receptors. Vision can seem normal at first, while blurred areas, dark spots, distorted shapes, or altered color perception appear later. The eclipse therefore creates a strange contrast. It invites careful attention to the sky at the same time that direct viewing requires strict limits. Safe observation begins with equipment designed specifically for the sun. Certified eclipse glasses contain filters that reduce sunlight to a safe level across visible and invisible wavelengths. They are far darker than ordinary sunglasses. Sunglasses are made to soften everyday glare, not to block the concentrated radiation of the solar disk. Wearing several pairs together does not turn them into solar filters. Smoked glass, exposed photographic film, compact discs, tinted plastic, and homemade darkened materials are also unreliable. Some may reduce visible brightness while allowing harmful ultraviolet or infrared energy to pass. A safe solar viewer must be manufactured for direct observation of the sun and must remain free from tears, punctures, loose seams, or deep scratches. Before use, the filter can be inspected in ordinary indoor light. Almost nothing should be visible through it except very bright sources, and the sun itself should appear comfortably dim and sharply defined. The glasses are placed securely over the eyes before looking upward. The observer then turns toward the sun. When the viewing ends, the face turns away before the glasses are removed. This simple order reduces the chance of an accidental unfiltered glance. Children require close supervision because the temptation to lift or shift the viewer can be strong, especially as the eclipse deepens. Proper fit matters as much as proper material. Light should not enter through a gap created by glasses that are too loose, bent, or poorly positioned. Direct solar filters also require special care when binoculars, telescopes, or cameras are involved. Eclipse glasses worn over the eyes do not make it safe to look through an unfiltered optical instrument. lenses collect far more light than the eye alone and concentrate it into a small area. This focused energy can damage the eye and can also burn through a filter placed behind the instrument. Telescopes, binoculars, and camera lenses need suitable solar filters mounted securely over the front. Where light enters, the filter must be intended for that instrument and must cover the entire opening. Viewfinders and magnifying optics should never be used with improvised filters. The instrument changes the amount and concentration of light, so a method safe for unaided viewing is not automatically safe when lenses are added. Indirect projection provides another way to follow the eclipse without looking at the sun. A pinhole viewer works because light passing through a small opening forms an image on a surface beyond it. A hole in a piece of card can project the solar disk onto another sheet, the ground, or a shaded wall. The image appears small, but the moon's changing silhouette becomes clear. During the partial phase, the projected sun turns into a crescent. The observer looks only at the projected image, never through the hole toward the sun. The opening is not an eyepiece. It is a simple lensless projector. Greater distance between the hole and the projection surface produces a larger image, though it may become dimmer and less sharp. Several small holes can create several suns at once. A kitchen colander, perforated card, or woven object may cast many crescent images. Leaves provide the same effect naturally. The small gaps between them act as pinholes, filling the ground with repeated copies of the eclipsed sun. This indirect method reveals the event through ordinary light and shadow, turning walls, paths, and sheets of paper into safe viewing surfaces. The partial phase lasts far longer than totality, so safe viewing habits must continue through most of the eclipse. The moon may take more than an hour to move from first contact to complete coverage. Throughout that time, direct observation requires a proper solar filter. As the sun narrows, the world may cool and the light may become strange, but these changes do not signal safety. Baily's beads are still direct sunlight. The diamond ring is still direct sunlight. Both are brilliant fragments of the photosphere passing through valleys along the moon's edge. They may last only seconds, yet those seconds occur before totality has fully begun or after it has ended. The glasses remain in place until the final bead disappears completely. Only within the path of totality, and only during the interval when the moon fully covers the photosphere, is the central eclipse safe to view without a solar filter. At that moment, the view through eclipse glasses becomes black because the glasses block the faint corona as well as the hidden solar surface. The sudden blackness confirms that the direct photospheric light is gone. The glasses can then be removed to reveal the corona, the dark moon, and the dimmed sky. This unfiltered interval is brief and belongs only to observers inside the umbral path. A deep partial eclipse outside the path never becomes safe for direct viewing. Even if nearly all of the sun is covered, a narrow surviving crescent is enough to require protection from beginning to end. Location therefore determines not only what the eclipse looks like, but whether there is any unfiltered viewing period at all. The end of totality requires the same attention as the beginning. The moon continues moving, and the photosphere eventually approaches the opposite edge. A bright point returns without warning if attention is elsewhere. Eclipse glasses must be replaced before that point appears. Experienced observers may follow reliable timing information and watch for the brightening of the lunar edge, but the safest principle remains simple filters return before direct sunlight returns. The first emerging bead marks the end of safe unfiltered viewing once it appears. The solar surface is exposed again, and protection remains necessary through the entire remaining partial phase. The surrounding landscape may still be dark for a few moments, but the eye responds to the concentrated light of the sun rather than to the general brightness of the environment. Clouds do not provide dependable protection. Thin cloud, haze, smoke, and fog may reduce visible glare while still allowing enough solar radiation through to cause harm. They can also shift quickly, revealing the sun at full intensity. A partially hidden sun should be treated in the same way as a clear one. Proper filters remain necessary. Reflections from water, glass, polished metal, or optical surfaces are also unsafe as intentional viewing methods because their brightness and filtering properties are unpredictable. Projection is safe because the observer watches an image formed on a separate surface, not because reflected sunlight is always harmless. Safe eclipse observation is built on a clear separation between direct and indirect viewing. Direct viewing uses a purpose-made solar filter. Indirect viewing uses projection and keeps the eyes turned away from the sun. Totality forms the only temporary exception, and that exception exists only when the photosphere is entirely concealed. The precautions do not reduce the wonder of the event, they make sustained observation possible. Through a proper filter, the sun appears as a calm, sharply bounded disk while the moon advances across it. Through a pinhole projection, the eclipse multiplies into crescents scattered across the ground. During totality, the filter is removed and the faint corona appears with a delicacy no ordinary solar viewer can show. Then protection returns as the bright surface re-emerges. The sequence follows the eclipse itself: filtered light, complete shadow, filtered light again. The alignment remains beautiful because its limits are understood. The same star that supports nearly every living system on Earth is also too intense for the unprotected eye. The moon can hide most of it without weakening the portion that remains. Safe observation respects that difference. It allows the eclipse to be followed from the first small indentation to the last returning curve while preserving the site through which the event is known. The age of total solar eclipses is temporary. The alignment seems timeless because the sun, moon, and Earth have followed their paths for far longer than human history. Yet the apparent equality between the solar and lunar disks is slowly changing. The moon is moving away from Earth. The change is small, only a few centimeters in an average year, but across immense spans of time it becomes decisive. As the distance grows, the moon appears slightly smaller in the sky. Total eclipses still occur because the lunar disk can presently cover the sun when the geometry is favorable. In the far future, that balance ends. The moon will cross directly in front of the sun and still fail to hide it. A ring of sunlight will remain around every central eclipse, and the moving darkness of totality will disappear from Earth. The moon's retreat is caused mainly by tidal interaction. Its gravity raises tides in Earth's oceans and also deforms the solid planet by a smaller amount. Earth rotates more quickly than the moon travels around it, so the tidal bulges are carried slightly ahead of the line between Earth and the moon. Their gravity pulls the moon forward along its orbit. That pull gives the moon orbital energy and moves it gradually outward. The exchange also slows Earth's rotation. Days become longer over geological time while the moon's orbit expands. Angular momentum, the measure connected with rotation and orbital motion, moves through the Earth-Moon system. A tiny change repeated across millions of years reshapes the clockwork of both worlds. In the distant past, the lunar disk appears larger than it does now. Total eclipses can be wider, and the sun may remain hidden for longer intervals under suitable conditions. Farther back, when the moon is much closer, the match between the disks is less delicate. The moon covers not only the solar surface but more of the inner corona. The narrow precision that defines modern totality belongs to a later stage in the system's evolution. The moon begins close enough to dominate the sky, then slowly withdraws until its apparent size approaches that of the sun. Earth now exists within this middle interval, when the match is close enough to reveal the corona and fragile enough to produce total, annular, and hybrid eclipses. the future change is equally gradual. No final total eclipse announces the approaching end to the whole planet. Instead, total events become less common as the moon's apparent disk shrinks. Favourable eclipses still occur when the moon is near the closest part of its orbit and Earth is near the farthest part of its orbit from the Sun. Under those conditions, the moon appears as large as possible, while the Sun appears slightly smaller. Eventually, even that best arrangement becomes insufficient. The umbral cone no longer reaches Earth's surface. Its tip ends in space above the planet, and the antumbra reaches the ground instead. Every central solar eclipse then becomes annular. Estimates place this transition hundreds of millions of years in the future, perhaps around 1 billion years from the present, though the exact date remains uncertain because tidal evolution is complex. By then, Earth itself will be profoundly different. Continents will have moved, oceans will have changed, and the Sun will be brighter than it is now as it continues its slow evolution. The question of who or what might witness the final total eclipse cannot be answered. Human beings occupy only a brief moment in planetary history. Species change, climates shift, and environments vanish long before the moon's retreat removes totality. The eclipse's future therefore opens onto a wider uncertainty. A precisely predictable geometry leads into a world that cannot be described in detail. What can be known is the physical form of the ending. On the day of the last total solar eclipse, the moon passes between Earth and the Sun under exceptionally favourable conditions. Its apparent edge reaches beyond the solar edge by only the smallest margin. The central shadow touches some narrow region of Earth, perhaps for only a brief interval. The corona becomes visible around the dark lunar disk. The landscape enters totality. Then sunlight returns. Later eclipses approach the same threshold but do not cross it. Their rings may be extremely thin. Lunar mountains may interrupt the sunlight into beads, creating moments that resemble the boundary of totality. Yet some part of the photosphere remains visible around the moon. The complete darkness never forms again. The disappearance of total eclipses also shows that rarity has more than one scale. At present, totality is rare at a specific location because the umbral path is narrow. Across the whole planet, however, total solar eclipses remain recurring events. In the far future, the rarity becomes absolute. There is no path of totality anywhere. No mountain, ocean, or continent enters the complete lunar shadow because that shadow no longer reaches Earth. Partial eclipses continue. Annular eclipses continue. The moon still crosses the Sun near its orbital nodes. The monthly phases still follow their rhythm. Only one expression of the alignment has vanished. The corona does not vanish with it. The Sun's outer atmosphere continues to spread through space, shaped by magnetic fields and the solar wind. It simply can no longer be revealed from Earth by the natural mask of a perfectly sized moon. Future observers, if any remain, may study it with instruments that block the solar disk artificially. Spacecraft already do this with devices called coronagraphs. Yet an artificial occulting disk is not the same planetary event. It does not send an umbra across oceans. It does not bring a false night to forests and cities. It does not place a black moon within a bright corona above the horizon. The scientific view can be reproduced, but the environmental transformation cannot. This loss belongs to the same slow process that has shaped Earth since the moon's formation. Tides influence coastlines, marine habitats, sediment, and biological rhythms. The moon helps stabilize the tilt of Earth's rotational axis over long periods. Its retreat changes the length of the month and contributes to the slow lengthening of the day. Total eclipses are only one visible consequence of that deeper relationship. Their eventual disappearance is not a separate catastrophe. It is a quiet stage in the continuing evolution of two connected worlds. The temporary nature of totality gives the present sky a special place without making it privileged in any cosmic sense. Earth happens to possess a large moon at a distance that now allows near perfect coverage of the sun. Other moons in the solar system cast shadows across their planets, and spacecraft have observed those shadows. Yet the close apparent match seen from Earth produces a particularly delicate eclipse, one that can hide the photosphere while revealing the corona. The effect depends on the present size of the sun in the sky, the present distance of the moon, and the present scale of its orbit. Change any of these enough, and the familiar form is lost. Every total eclipse therefore carries two movements. One is fast, the lunar shadow races across Earth. Totality arrives, and sunlight returns within minutes. The other is almost motionless, the moon recedes a little farther. The days lengthen by an immeasurably small amount, and the future balance shifts. The brief darkness belongs inside that enormous change. Each event is one more occurrence in a sequence that began under a larger moon and ends under a smaller one. For now, the shadow still reaches the ground. The sun and moon still appear close enough in size for the bright surface of a star to disappear behind a rocky world. The corona still emerges around the lunar edge. Animals still respond to midday darkness. Temperatures still fall, and a narrow path still crosses the planet like a temporary river of night. Yet the alignment carries its own ending within it. Tidal forces are already moving the moon outward. The final total eclipse is not waiting for a sudden disruption. It is approaching through the same calm and predictable motion that creates every eclipse before it. Long after the present continents have changed, the moon will continue to pass across the sun. A bright ring will remain, complete and unbroken except where lunar mountains shape its edge. The sky will remember the geometry but not the darkness. Totality will belong to planetary history, like ancient oceans and vanished species, real but unreachable. In the current age, however, the match remains. A shadow can still extend from the moon, cross empty space, and touch Earth for a few minutes. Daylight can still disappear beneath the rare alignment of three worlds.